Hello students, welcome to the channel. Today we'll walk through a reading passage. This is the third passage in the 2019 PSAT, October 16, 2019 PSAT. This is a science passage, so let's begin. This passage is adapted from Dennis Normil, Close Look at Young Star Finds a Chemical Surprise by American Association for the Advancement of Science. So from the blurb, we know that this is a passage from astronomy, and a lot of science passages are taken from the American Association for the Advancement of Science. So you should try and read journals like Nature, Science, etc. to get more familiar with the kind of passages that come on the SAT. The basics of star formation are easy. Find an unusually dense region within a molecular cloud filled with dust and gas in interstellar space and let gravity do the rest. The gas and dust will eventually coalesce into a donut-shaped envelope that encircles an inner rotating disk. As material accumulates over hundreds of thousands of years, the central region collapses into a star while the disk solidifies into planets. So this is describing the way stars are formed, right? So that is the introductory paragraph, which tells you that if there is a dense region filled with dust and gas, then gravity will make sure that that coalesces into, into a mass, into a donut-shaped envelope, which will encircle a rotating disk. And over time, the central region will collapse into a star and the disk will become planets. Astronomers have understood this overall scenario for decades, but the details are fuzzy because telescopes haven't been good enough to check theorists' computer models. That changed in 2011 with the partial completion of the Atacama Large Millimeter Submillimeter Array, ALMA. The telescope, a collection of radio antennas, is being erected on the Chajnantor Plain, 5,000 meters above sea level in the Chilean Andes, where the dry, sparse air causes minimal distortion of the faint waves from the far reaches of the universe. Using 24 of the antennas, the final array will have 66. An international group led by astrophysicists at the University of Tokyo has taken the most detailed look yet at the heart of a star-forming region and found a chemical surprise. So this paragraph presents the advances in technology that have finally allowed scientists to kind of verify experimentally, not experimentally, but verify what they have long assumed about star formation. And the ALMA, which is mounted in the Chilean Andes, has thrown up a surprise, a chemical surprise. The researchers trained ALMA on a very young star still forming in the constellation Taurus, about 450 light years from Earth. As is typical at such an early stage, the star is encircled by an envelope and disk of gas and dust. The new telescope's power enabled the team to identify the chemical composition of the gases at different locations throughout this star and planet-forming system. Previously, astronomers thought that this envelope and disk must be made up of the same gaseous molecules of hydrogen found throughout interstellar space, plus dust particles made up of other elements. To the surprise of the University of Tokyo group, ALMA detected something different, sulfur monoxide gas, in a narrow band where the envelope meets the disk. Collisions between particles in the envelope and those in the rapidly spinning disk generate heat that thaws frozen sulfur monoxide molecules stuck to dust grains, explains Nami Sakai, an astrophysicist at the University of Tokyo. Sulfur monoxide can't be detected when it is frozen to dust grains, but ALMA can spot it in gaseous state. Knowing just what gases are swirling around young stars should lead us to a better understanding of where and how elements found in planets, comets, and asteroids are formed. Saki and colleagues report their findings online at Nature. So this describes the observation, right? The observation was that, the assumption is that if there is a planet in its early stages, the cloud of gas and dust that encircles the planet would be primarily made of hydrogen. But in this case, in the case of this tiny star, ALMA detected sulfur monoxide that had been thawed, that had kind of turned into gaseous state from frozen sulfur monoxide, which are stuck to the dust grains. And that is something which was new, which was unexpected. These are beautiful data and very interesting results, says Evine van Dishoek, an astrophysicist at the Leiden Observatory in the Netherlands. This work shows that ALMA will provide ample observational evidence that will challenge theoretical models, adds astrophysicist Stéphane Guilletou of the University of Bordeaux in France. This paper is a beautiful example of the new discovery capabilities offered by ALMA. So the fact that sulfur dioxide could only be detected because of ALMA, the fact that ALMA can spot it in the gaseous state, is a huge advance for the study of star formation. And the last paragraph kind of credits ALMA with the ability to now learn a lot more about how stars are formed. Okay, so let's question number 20. A central idea of the passage is that the ALMA telescope has provided new details about the composition of gases around young stars, is limited to observing stars that are less than 450 light years from Earth, has found that there are too few hydrogen molecules in interstellar space, allows astrophysicists to determine the density of stars as they form. So here the right answer is very obviously A, that because we know that ALMA studied this young star in the constellation Taurus, and it found that there was sulfur dioxide in the gaseous cloud, right? So that is what A supports. B is not supported by the passage. Yes, the star that it is studying is 450 light years from Earth, but there is no mention in the passage that ALMA can only study stars at that distance. Option C is not correct. The question is about the gaseous, so to say, state of young stars and the cloud that encircles them. It's not about interstellar space. And the density of stars is not what ALMA has helped with, right? So D is wrong as well. The image of a donut-shaped envelope in line 5 mainly serves to, so if you go back and read line 5, it says the gas and dust will eventually coalesce into a donut-shaped envelope that encircles an inner rotating disk. So the idea is to kind of make it more relatable, right? Help readers visualize an unfamiliar situation, describe a tool used in a field of research, introduce humor into what is otherwise a serious scientific discussion, characterize the limits of current scientific knowledge. So it's obviously A here. You can clearly eliminate B and D, right? There is no tool that was used when the description of donut-shaped envelope was included. And it doesn't indicate the limits of current scientific knowledge, right? Those are just completely out there options. Now between A and C, A is better because donut-shaped envelope is not humor. That's not introducing humor into the passage, right? So it's helping readers visualize a situation that is unfamiliar to them. As used in line 12, check most nearly meets. So let's look at 12. Telescopes haven't been good enough to check theorists' computer models. So to kind of verify, right? Verify is a good word. To confirm is a good word. Maintain, adopt, obstruct, or verify. So we have verify in the options. We are kind of saying that the telescopes so far haven't been able to confirm what theorists have predicted about star formation. So none of the other words make sense in context here. So D. According to the passage, what is an advantage of placing ALMA at a location high above sea level? So the answer for this comes from here, right? That this telescope is being erected on the Changnanta plain, 5,000 meters above sea level, where the dry, sparse air causes minimal distortion of the faint waves from the far reaches of the universe. So far above the sea level, the air is so dry that you can obtain, or you can get the faint waves from the farthest reaches of the universe with as little distortion as is possible on Earth. So there are few distractions from work at the remote observation site. There are fewer disturbing effects caused by Earth's atmosphere. Reflection of sunlight off the ocean is minimized at that altitude. Distances to star-forming regions are slightly reduced. So it's very clearly B, right? There are fewer disturbing effects because the Earth's air there is dry and sparse. It has got nothing to do with distractions from work or reflection of sunlight. And distances to star-forming regions, I mean, that's minuscule, right, compared to the regions we are talking about. So D is just funny. Okay, as used in line 29, stage most nearly means. So we have, as is typical at such an early stage, the star is encircled by an envelope and disk of gas and dust. So at an early stage, at an early, let's say, what's a good word to replace it? An early part of the process, at an early, let's say, at an early point in the cycle of formation, in the process of star formation. So phase, phase is a good option because a phase is like part of a process, right? So at an early phase. Platform doesn't make sense because we're talking about a time period and an early time in the formation of a star. So platform doesn't fit there. And even portion and place don't convey the sense of time period. So A is the best answer. Based on the passage, in which region surrounding other young stars should astronomers search if they wish to confirm the discovery around the young star in Taurus? Which region surrounding other young stars? This has to be evidence, right? So why don't we work on the evidence first? So, okay, I'll just write 25 and here and 26 here. Yeah, this is so crazy. Okay, so let's just look at 4 to 6, 30 to 33. And 38 to 41 and 48 to 51. So which part should scientists study, right? So I'm not sure 4 to 6 is relevant. So we'll just quickly look at it. The gas and dust will eventually coalesce into a donut-shaped envelope that encircles an inner rotating disk. Is that possible? We'll see. Okay. Okay, we'll come back to this. 30 to 33. The new telescope's power enabled the team to identify the gases at different locations. So it's definitely not B. 38 to 41. To the surprise of the University of Tokyo group, ALMA detected something different, sulfur monoxide in a narrow band where the envelope meets the disk. Okay, so I like this narrow band where the envelope meets the disk. And 48 to 51. But ALMA can spot it in the gaseous state. Yeah, this is not relevant. So I like 38 to 41. The rapidly spinning inner disk, the central section of the envelope, the area of contact between the disk and the envelope, the boundary where the envelope meets the interstellar space. So it's C, right? Because 38 to 41 is telling me that ALMA detected sulfur monoxide in a narrow band where the envelope meets the disk. So the envelope and the disk. So 25 is C. And 26 is also C. It was 38 to 41, right? That's where we, yeah. Right, let's go to the next one. The main purpose of the third paragraph, line 26 to 52. So this entire paragraph, right? The researchers trained ALMA on a very young star it goes on till here, is to kind of describe how this surprising finding was arrived at, right? Right, they trained Alma on this star, and then they studied, and then they were not, they expected something, but then they found sulfur monoxide. So it's kind of, yeah. Describe how dense molecular clouds acquire dust and particles from interstellar space. Inform readers that scientists find gaseous hydrogen in all regions of interstellar space. Introduce the technique used to build telescopes such as ALMA. Describe what ALMA enables scientists to discover near a newly formed star. It's very clearly D, right? So here I think you can very obviously eliminate options A and B, because that's not the point, right? The point is what ALMA did. And C is not correct because it's not about building the telescope. And it's certainly not about building telescopes such as ALMA. ALMA is like one of its kind. It's like the first of probably new generation of telescopes. So C is not correct, while D, because the paragraph talks about how ALMA helps scientists make this discovery. So D is the best answer. Okay, 28 and 29 is an evidence pair. Based on the passage, what can reasonably be inferred about how astrophysicists view ALMA? They believe that using it may yield a great deal of surprising data. They do not think that they will be able to improve the technology on which it relies. They worry that it is not powerful enough to determine the composition of dust particles. They think that it will be quickly replaced by a more sophisticated array. So I think it's A, right? I just need to confirm the surprising data part, because the last paragraph was almost entirely focused on the benefits of ALMA. So I like A, but let's just confirm that. So 20 to 25, 20 to 25, 26 to 28, 53 to 55, and 60 to 61. So I'll first look at the last two options, because those were where the answer could be found about what ALMA can do. So 53 to 55, these are beautiful data and very interesting results. And this paper is a beautiful example of the new capabilities offered by ALMA. Okay, so it's definitely D. For 29, it's D. 20 to 25 has taken the most detailed look yet. So this is what ALMA has already done. The researchers, and this is how the researchers trained ALMA, right? So I like D for 29. So the beautiful discovery capabilities, right? The new discovery capabilities. So it's not about replacing it. It is not about not being powerful enough. Yeah, it is A. So 28 is A and 29 is D. Okay, so that was question 20 to 29. Let's grade this. Okay. October 16, yeah. Okay, 20 to 29. AADBA, AADBA, 25, CCDAD, CCDAD. Okay, so those were all correct. Hope this exercise was useful. If it was, hit like and subscribe to the channel. Let me know what other videos you'd like me to upload. I've already uploaded the reading walkthroughs for the first two passages of this test, so be sure to check them out. I'll see you guys in a new video soon. Take care. Bye-bye.